Hi, Srini. Have a busy day, eh?
Hello.
Hello, hello.
Hello.
Hello, hello.
Hi, good afternoon, sir.
Good afternoon. Have a busy day, eh? Okay, anything you want to ask before we start? Anything from
No,
yesterday?
sir, I'd like to continue. I want to know about the nuclear thing.
Anything that is not clear that you
Quantum.
want? Hmm?
I'm not sure I understood the thing. You can go on, sir.
Okay.
I can continue, sir.
Yeah, just review through some of the things that we have learned yesterday. Right? That's how we represent the photon. Not exactly a wave, but it's a wave with different amplitude, if you like. Right? This one you have to know. What is a photon? Packet or quantum of energy of electromagnetic radiation. And the energy of the photon is given by E equals to HF. F is a frequency, H is Planck's constant. Right? So most often you'll be using this one, HC over lambda. And the other thing that you will need to remember would be okay, can you remember that? The laws of photoelectric emission or observations? Can you remember? Okay. R is for rate of emission. I, instantaneous emission. T is threshold frequency. K is what? K is kinetic energy. Usually it's maximum kinetic energy.
Maximum kinetic energy.
Rate of emission of electron depend on intensity. Instantaneous emission of electron when metal is illuminated by radiation. Right? Straight away, as soon as you shine the electromagnetic radiation on the metal surface, the electron is emitted, threshold. Right? That means the radiation must have a threshold frequency, must have a frequency that's higher than the threshold frequency for emission to occur. Maximum electron kinetic energy depend on frequency of electromagnetic radiation. Maximum electron kinetic energy does not depend on intensity, right? Depend on frequency, but not intensity. Okay, let us carry on with okay, yesterday we the other thing that we'll be using is this equation, Einstein's photoelectric equation. That's your Kmax. Rather than then use that, we can use W.
More than work function. Yeah.
Okay, so that is the maximum kinetic energy of the emitted electron. That's the energy of the photon. So that's the work function. So for emission to occur, the energy of the photon must be greater or equal to the work function. Where it's equal to the work function, then this is zero. It's emitted, but with zero velocity or kinetic energy. Okay, so that essentially explains most of the observation. Then we look at the equation, right? How where we change the frequency for frequency of electromagnetic radiation falling on the metal, we can determine the maximum kinetic energy. And we say that from this equation, it's a straight line graph. Gradient is h, Planck's constant. And then the y-intercept is your work function. And that point there, where your y equals to 0 or 0 kinetic energy is your threshold frequency. Okay, let's go further. Why are electrons emitted with a range of velocity that is from 0 to maximum? Any idea? Any idea why are electrons emitted with a range of velocity that is from 0 to maximum? Okay. Electron at the surface of metal will be emitted with maximum kinetic energy or maximum velocity. Electrons further in, as they receive energy from the photon, is subjected to retardation. Further in, they still emitted with maximum kinetic energy, but remember, as it tries to escape from the metal to the metal surface, there are positive ions that is retarding it, right? So there's a retardation, slow it down by the positive ions. Thus, the kinetic energy of the electron emitted would depend on the position of the electron on the surface. If the electron is further from the surface, deeper down, then it will escape with smaller kinetic energy. If it's at the surface, it would escape with maximum kinetic energy. The electrons are emitted with a range of velocity. Okay, anything that's not clear? I hope you're not.
Give me 1 minute, teacher. Teacher went a bit further. I just want to read and then understand it. Teacher, what they meant by electron further in as they receive energy from the photon would be subjected to retardation. Oh, that means you slow down,
Yeah, it's surrounded by positive ion as you go up to the surface. So there is a retarding force.
Okay.
This diagram just show you. There's a attractive resultant force pulling in. That's the velocity.
Yeah.
So it has to be slowed down before it escapes. So the further in, the smaller will be the velocity. Nearer to the surface, the greater will be the velocity of kinetic energy. Electron at surface escape with maximum kinetic energy because there's nothing to stop it. Right? It has 0 kinetic energy. You receive photon from the electromagnetic radiation, it just escapes with maximum kinetic energy. Electron further in, escape with lower velocity due to retardation. Right? There are positive ions, so there is your retarding force. As it moves to the surface, electron further in the metal escape with smaller velocity or kinetic energy. Okay. Any comment? If not, get your worksheet ready. We'll do some calculation. Okay. Calculate this one.
Wait, sir, go back, sir. 1 minute. Oh, sir, that means when they are not so near and they are very far, it's a very slim chance for them to escape light, sir, right?
Is subjected to retarding force. By the
So
attractive
if it's a
force,
smaller retarding force, then it's easier to escape a bit.
if it's further in, it experiences more force, greater
Yeah.
value of the force. So when it's so it cannot escape with large velocity. Velocity will be quite small, depending on how deep it is in the metal.
And how big the retarding force is. So yeah, okay.
Okay, try this question. We are just using this
Yeah.
number 3
Sure.
in the worksheet. We are just using this formula. Getting you to be familiar with the conversion from Joule to electron volt. Okay, what is the answer for A? You have to convert it to Joule first before you can do any calculation.
Okay.
'A given work function, convert it to Joule.
Yeah. 6.24 times 10 to the power negative 19 joule, teacher.
Okay, good. Calculate the threshold frequency and wavelength.
Okay.
And you get the frequency.
Yeah, 1 minute answer.
And make sure you bring your value of constant every time you come for class. So you can refer to where to get the answer. Can you get the answer?
Oh, Chad, you don't use that formula, Chad. K max equals to HF minus W.
No, we are not
No,
using that yet. You are just working with work function, that's all. You must know how to get your threshold frequency from work function.
Oh.
I'm trying to get you to familiarize yourself with your formula. How to relate work function and threshold frequency.
Yeah, okay, I got it, teacher.
Then wavelength. Right, this is the threshold wavelength or maximum wavelength. Can
Can je?
Which part of the electromagnetic spectrum is this wavelength?
Which part of the electromagnetic spectrum is this wavelength?
Hmm.
Oh, you're asking me which type?
The ultraviolet, infrared, visible, or gamma ray, or X-ray, or radio wave. Right? You must know your visible light. Visible light is about 400 to 800 nanometer. So this one is in ultraviolet. Okay. Now can use your formula to calculate your part C. Calculate the maximum kinetic energy of the electron emitter when 300 nanometer radiation falls on beryllium. I can use the formula now. What's the answer?
1 minute, teacher. Sure, 3.9 times 10 to the power -20, teacher.
Huh? How do you get 3.9? We have can't careless mistake again.
Hey, Che, I also type in the same thing, lah, Che.
And why I get wrong answer?
Maybe I typed somewhere calculation wrong, I think. Wow, give me just 1 minute, Che. But I did the same way like you did, teacher. But I don't know how my calculator showed something wrong.
No, of course, there's carelessness. You lose unnecessary mark. Can get the answer?
I can get the answer, teacher. I did get the 6.63 times 10 to the power -19, but then when I minus it in the calculator, it's showing me something else.
Huh? Don't tell me I got it wrong.
Yeah.
What do you get? What is the energy for?
HF.
Right? You have got this answer.
Yeah, I got. But then suddenly it's showing me the calculator differently.
624. Maybe I did wrongly.
Or maybe I can't type in directly. Maybe.
If you have got this correct, you got this
Yeah,
correct.
I got it correct.
Then you can just subtract only.
Yeah, I subtract in the calculator, put bracket also, I still don't want to come.
Oh, 39, maybe you're right. You're right. Because I think you use 4. You use 4 here.
I put 6.24 lah.
Ah, that's why. I am the one who made the mistake. I round it off too early.
Oh, and then my one is power -20 teachers. 3.9 times 10 to the power -20.
That one is okay. It's a matter of changing the power.
3.9 times 10 to the power
Yeah,
of
you're right.
20.
You're right. Yeah, right. I'm the careless one.
Okay.
Okay, good. You can calculate. This is a simple one. You should be able to get the mark there. Common question. Okay, let's review your electromagnetic waves.
So 1 minute, go back again, sir. Okay, sir, can continue.
Okay, let's review your electromagnetic wave on intensity. Intensity is the energy per unit time, right? Yes. Energy divided by time. No? Falling normally must be perpendicular to the surface, like here. Per unit area, that's why we divide by area. That is your surface area. That's the beam of radiation on the surface, right? So that's our equation. Intensity is power divided by area. That's the area, or energy divided by time divided by area, right? And then the intensity is proportional to amplitude square. So in order to increase the energy, we increase the amplitude. Right? So increasing intensity increases the energy given to electrons. Right? It's just like, remember, the wave is very small, the electron is also very small. So in terms of electromagnetic waves, it's just like heating. Right? If the energy is given to the metal, it heats up the metal, so the electron will gain kinetic energy. So if you give more energy, increase the intensity, more electron will escape. Right? Rate of emission increases. So yeah, you can explain. Electromagnetic theory can explain the rate of increase. The rate of emission increases with intensity of the radiation. Okay. Increase the intensity, increase the energy given to the electron. So more electron can escape. That explain your 4A. Right? Rate of emission increases with intensity of radiation. Okay. I'm just referring to here.
Yeah, give me 1 minute, sir.
I'm just referring to all these. Yeah, that's all. I'm referring to all that, that's all. That's your 4A.
Oh,
That's all. If you want, you can take a
okay.
photograph of it so that I can refer to it as we go along.
Yeah, sure. So go back again. I mean, go back to the current slide, the one which we just stopped. I just want to. Intensity is the energy per unit time falling normally per unit area. So energy falling, is it, teacher, based on the surface area? Is that it?
You have done that under electromagnetic radiation. You have teach you that intensity. Okay.
Okay. So isn't it inversely proportional? You just put proportional only. So,
Proportional to amplitude square. Inversely proportional to distance square. Distance square, don't get confused. Amplitude square. You should start revising your work already. If you are going to.
Square. Yeah.
Okay. You study under sound waves. Okay, let's go for the. So what wave theory tell us is that we can increase the amplitude, increase the
Yeah,
energy
okay.
given. So no matter what type of radiation we shine on the surface, electrons should still be emitted. But that's not true. Foci tells us there is a threshold frequency. Whereas electromagnetic wave theory tells us there's no need for threshold frequency. I increase the intensity, I increase the energy given to the electron will escape. Okay? So that's the weakness of electromagnetic theory. You cannot explain why you have threshold frequency. Yeah, what's the problem? Yep. What's your problem? Talk to me. What is your problem? Ask whatever you don't understand, ask. Okay. Any question? Anything to ask? Anything that is not clear?
Uh,
Okay. Electromagnetic wave theory cannot explain to us why there's a threshold frequency. It just say that I increase the intensity, I increase the energy, the electron should be emitted. There shouldn't be a threshold frequency at all. Any radiation I shine on the surface of metal, I just increase the amplitude as well. So I increase the energy falling on the surface as well, which is not true. Yep, what's the problem?
okay.
Quantum theory. What's the difference? To explain photoelectric effect, above, we imagine that electromagnetic radiation exists as photon of fixed or packet of energy, depending on the frequency. The energy is given completely to the electron when the photon meets the electron and the photon disappears. Not all photons will meet an electron. Some pass through the metal without interaction. Okay, so that's the energy of the photon depending on the frequency. Intensity of radiation now, well, still the same formula, but depends on energy of photon, number of photon falling on the metal surface. Right? So we are still using the same formula, but now we have to replace the total energy, right? Because there has this photon, each photon has a fixed energy. So the number of photon falling is the total energy divided by time. Right? So the power now becomes your total energy divided by time. Total energy is the number of photon times energy of each photon. Okay, and P over T is number of photon per second falling on the surface. E is the energy of photon. So that explained to us threshold frequency. Okay. So we can see that our intensity now depends not only on the energy of the photon, but depends on the number of photons per second falling on the surface. So if we use the same energy, same photon, right, we increase the number of photons falling, then the rate of emission of electron will increase. That's your 4A. Rate of emission of electron increases with intensity of the radiation falling on the surface. Can anything not clear?
Okay, so that means practically it's just these two factors, energy of the photon and number of the photon for the intensity of the radiation. Without these two, cannot lah. So yeah.
We will look in that, no problem. We will go into more detail. Okay, we just repeating, that's all. Okay, so that is our intensity. It's just a power divided by area. And then the power is just your NPE times T. So increasing the intensity, but keeping the frequency of the electromagnetic radiation constant, we are increasing the number of photon on the energy, not the energy of the photon. Okay, let's look at the equation. That's the equation. Right? That's what we are looking at now. Easier to look at the equation rather than look at the wording there. Right? We write that MPT cross-sectional area. Okay, this tells us we keep our frequency constant. So the energy of the photon is constant, E is constant. Right? Because our F is constant. Then we increase that, increase the intensity. Your A is constant. So it means that if you increase the intensity, NP over T must be increased. Right? The means rate of photon falling on the surface must increase. Okay with that?
Okay.
Likewise, if the number of photons falling on the surface is constant, but the energy of the photon is increased by increasing the frequency, the intensity of the surface is increased. Right? Same thing, same equation. Right? We are keeping NP over T constant. Right? Area is constant. Right? Area is constant. And then we increase our energy of the photon by increasing the frequency. So we can see the intensity will increase. Okay. So we can increase intensity either by increasing the energy of the photon or increase the number of photons falling on the surface. Anything not clear? Yep, what is not clear?
Oh, just give me 1 minute. Oh, okay.
Yeah, we're keeping this one A constant, area constant. We're keeping MPT constant, number of photons falling on surface constant. But we increase the intensity. So it means that we must have increased the energy or the frequency of the photon. That's all.
Okay.
Okay, let's just summarize comparing wave model and quantum theory. Rate of emission electron depend on intensity. Greater intensity, greater emission. Wave model, greater intensity means more energy given to the metal, so more electrons can escape, which is true. Photon model, wave intensity means more photon per second falling on the metal, so more electron released per second, which is true. Okay. Yep. What's the problem? We are just explaining 4A, that's all. If you are tired, the next time don't come for tuition, right?
No, I'm not tired. I'm understanding it, teacher. Just it's okay. Yeah, I understand, teacher. Okay.
Instantaneous emission of electron when metal is illuminated by radiation. Wave model, as the wave meets an electron, it gives energy. As sufficient energy is received, the electron is emitted. It takes time for electron to be emitted, which is false. Right? As soon as you shine radiation, electron is emitted. But wave model is different. Wave model is just like our classical physics. It takes time for a pot of water to boil. You have to add what energy heat until it increase the temperature, then it boils. So that's what wave model is saying. I give you energy, you receive energy, then it takes some time for the electron to emit, which is not true. Right? Photon model, each photon has a fixed amount of energy. If the energy is sufficient, right, as long as it's greater than the work function, the electron is emitted straight away. There's no time lag. Instantly, it is emitted. Okay?
Okay.
So that one wave model cannot explain. There is a threshold frequency below which no emission. Right? So for emission to occur, the electromagnetic radiation must have a frequency greater than the threshold frequency. Right? Whereas wave model tells us low frequency light should work as we can increase the amplitude to increase the intensity. Electrons can be released more slowly. Right? We shine whatever radiation we shine on the surface, even we just need to increase amplitude to increase the intensity. So more energy is given to the metal, to the electron. So electron should be released slowly, that's all. Right? Which is not true. You can increase the intensity. If it's below threshold frequency, the radiation won't cause any emission. Photon model, as energy is lower than the work function, no emission. That's all. Anything which is not clear? Not clear, you speak to me. I explain to you. Okay, if not, let's carry on. Maximum electron kinetic energy depend on frequency. Greater frequency of electromagnetic radiation means greater intensity. More energy given to electron, so electron escape with greater kinetic energy. Which is true. Except you have to qualify greater kinetic energy, correct, but it cannot keep on going further. Right? There is a maximum kinetic energy, no greater than maximum kinetic energy. Higher frequency means photon of higher kinetic energy for an electron. So electron gain more energy and can escape with greater kinetic energy. Okay. Any comment? Yeah, we are just using this formula, that's all. As long as the frequency of the electromagnetic radiation, right, the energy is greater than the work function, it will escape with maximum kinetic energy. It cannot be any more greater than that. Okay.
The screen.
Yep. I think this one should be false. Because this one wave model will tell us that there is no maximum kinetic energy. I just increase intensity, and then the kinetic energy will keep on increasing, which is not true. Okay.
Hello, sir.
Yeah. What's the problem?
No, sir, the internet suddenly keep going off and going on, sir. Internet problem.
Okay.
Yeah, now, okay, sir, can you go like 2 to 3 slides previous, please?
Say again.
Go back like 2, 3 slides, sir.
You are getting very slow like that.
Teacher is the one going too fast. I'm trying to understand.
I'm not
teacher
going too
keep
fast. You're
going.
too slow. This teacher have teach you in class already. Now I'm doing a second time.
Teacher, he'll just keep talking only. Nobody understands the thing.
Yeah, can understand, see?
Okay, can understand.
Okay, that's for part B.
Okay.
Maximum electron kinetic energy does not depend on maximum electron kinetic energy, not depend on intensity. Wave model will say greater intensity would mean electron escape with greater kinetic energy, which is false. That's the maximum kinetic energy. Photon model, maximum kinetic energy of electron would depend on energy of the incident photon. That's the equation. That kinetic energy maximum depends on that frequency. That's all.
So what you put there false for?
Say again.
No, you put there false. What is that for?
False. Wave model cannot explain this truth. It cannot explain this fact there. So that's why I put false. Wave model is saying you can still increase the intensity, you give more energy, so the kinetic energy should be greater and greater, which is not true. There's a maximum kinetic energy.
Okay.
Okay, experiment to measure Kmax with frequency. Right, that's your photocell. That's your cathode. Right, anode is just a conductor, that's all. That's the symbol. Normally, you don't need to draw 3 dimensions. I just draw the symbol to represent your photocell. Why is the cathode not flat? Why is it curved like that? Any idea?
No.
I remember the electron are emitted. If it's flat, not all of it will reach the anode. Right? You want all the photon, if possible, to converge on the anode. Right? So the cathode emits electron and converts the electrons to the anode. Right? So a photocell or photoelectric cell is an evacuated transparent glass bulb enclosing 2 electrodes. So inside there is vacuum, very little air, right? Vacuum, and there's 2 electrodes, cathode and the anode. Anode, the anode, or sometimes we call it collector because it collects the electron, which is usually maintained at positive potential. It collects the electron from the cathode. And there's your cathode, right? Or sometimes we call it emitter, which is made up of photosensitive metal, usually is negative potential. So the cathode we call emitter because it gives out electron. Okay, to investigate how the current passing through the cell depends on the PD across the cell. Right, that's the ultraviolet ray coming in. We want to know if we keep ultraviolet light constant, same intensity, same wavelength, then we increase the potential. Right? How does the potential and current changes? So that is your cathode made of zinc. To increase the voltage, read the voltmeter. That's a voltmeter. Right? That is a symbol for variable power supply. And then read the microammeter. We have to use microammeter because the current is very small. Then after that, we reverse this one. Right? Now we have the cathode is positive, the anode is negative. With power supply reverse, here the cathode is positive. So as the electron is emitted, it's pulled back. Remember, we are now pushing back the electron. This to determine the stopping potential. Okay, so that's our aim, to investigate how the current passing through the cell depends on the PD across the cell. The independent variable, what you change is the voltage. You change the voltage. Depending variable is the current measured using the microammeter. Control variable, what we keep constant, use monochromatic light of known and constant wavelength and constant intensity. Photocell is illuminated with electromagnetic radiation of a particular frequency and intensity. The PD across the cell is increased and the microammeter is red. Repeat with the polarity of the cell reverse. Okay, so that's the experiment. Remember that's your potential divider, this one. All right, we want to change the potential across there, voltmeter to read, and then microammeter to read the current. Connection to the cell can be reversed. This is what we do just now. Right? We reverse it. This is where you want to find stopping potential. When the electromagnetic radiation falls on the emitter, that's the emitter, the cathode, electron is emitted, and these are attracted. If this is positive anode, then the electron will be collected by the anode, and then it will flow as a current detected by the microammeter. Okay. Okay, so what type of graph do we get? we are plotting the emitter reading or microemitter reading against voltmeter reading. Right? When the anode is charged positive, right? This is the case, the first part. After that, we use this second part. Okay, that's the curve that we get. Right? When the anode is positive potential, with respect to the cathode negative potential, electrons are accelerated to the anode. Right? Basically, you are collecting the electron. As the potential on the anode increases, if we look at the graph, right? This is zero potential. Zero potential, we still got current. Why? Because the emitter still, the electrons are emitted with a range of velocity. So those that have velocity will be collected by the anode. Then as you increase the anode potential, more and more electrons will be collected. Those that have zero energy will also be given energy and move to the anode. Current is now maximum, right? It will reach maximum. What does it mean? We call it saturation current. Okay, so that is your zero potential across the cathode anode. So most electron with kinetic energy and moving in the direction of anode will be collected. Right? At this part where the current is constant, the rate of electron emitted equals to the rate collected. Remember, the number of photons falling on the surface is constant. So the number of electrons emitted is also constant. So if you collect all the electrons, there's no more extra. So what is emitted was collected. So that's why the current is constant. Right? This is the case where we put a cathode constant for this part. So as you increase the negative potential, more and more electrons are pushed back into the cathode. So the current will decrease until you have your minus Vs. Electron emitted by emitter are pushed back into the emitter. Okay, anything not clear?
Just give me 1 minute, teacher.
Okay. Right? Remember, the electron are emitted with a range of velocity. So as you increase the potential, more and more electrons are collected. So that's why the current increases. Right? The current cannot keep on increases because the number of photons falling on the surface is constant. Number of electrons emitted per second is also constant. Yep. What is the problem?
I'm just reading, teacher. Just 1 minute. Okay.
Okay, just explaining the same thing to you. The current is constant because there's no other source. Number of photons falling on the surface is constant. Number of electrons emitted per second is also constant. When the anode is negative, potential with respect to the emitter, electron emitted by the emitter is pushed back. That's what we are just repeating, that's all. Since electrons are emitted with a range of velocity, As the collector becomes more and more negative, less and less electron. So as you increase the negative voltage in this case here, less and less electron will be collected. So it means the current decreases until at minus Vs, then the current is 0. So that's where we define our stopping potential. At a particular voltage called the stopping potential, or some people call it cut-off voltage, no current will be detected. So we define stopping potential is the negative voltage that must be applied to stop all electrons from reaching the collector or anode. Okay, so we are just using our work done equals to V times Q. Right? Work done to stop electron of rest mass M and speed V max through a potential difference of Vs is just given by kinetic energy. Maximum kinetic energy equals to the work done. Right? Or we call loss in kinetic energy equals to work done. Right? Since Vs depends on maximum kinetic energy, thus its value is dependent on energy of the radiation. Okay, that's all. This formula. Memorize this formula. And now, what is stopping potential? Right? Memorize this one. What is stopping potential? Okay, I just review to you what we have learned yesterday. Maximum kinetic energy. Right? That's the equation, Einstein's photoelectric equation. We say that it's a straight line, right, with a y-intercept. Gradient, right? Gradient is your h, Planck's constant. Y-intercept is minus work function. And your x-intercept, which is here, is f naught. Okay with that? Anything not clear from yesterday? If not, I'm going to ask you some question now.
Yeah, okay.
Okay, now we are going to draw Vs against frequency. On the graph, mark the threshold frequency. Catch the graph of stopping potential versus frequency graph. How does the graph look like? Yep.
Okay, y-intercept, okay, gradient represent is h.
Is it a straight line or a curve? Or a line passing to origin? What does the graph look like?
Straight line. You know, line
Yeah.
passing through origin, line passing through origin, but the y-intercept minus the thing, that's why it went down. So, yeah.
Okay, got passing through origin. It got y-intercept means it got y-intercept. Doesn't pass through origin. That's all.
Sorry, no. Sorry, no, it doesn't pass through origin. It intercepts the negative y-intercept. Yeah. Yes, it's a
What
straight
does
line.
the y-intercept represent?
Phi. That one, the very weird symbol. I forgot the name.
What does the gradient represent?
H.
What does the x-intercept represent?
X-intercept represent the frequency.
You got only one right out of 3. Yeah, because you're not applying your knowledge. You have just learned the knowledge. I don't apply. I look at the physics involved. That's the equation we are using. But we are not plotting this graph. Right? You're replacing your EK max with EVS. and then rearranging because we want Vs against our frequency. That's the equation. Right? Replace that EK max with EVS. So divide by E, you get Vs. So this one divided by E, this one divided by E, and compare to equation of straight line. Right? Vs is your Y, F is your X. So that is your Y-intercept. Right? So gradient is just your H over E. Y-intercept is W over E. That's all. Okay. Any comment or any question? We are more or less completed. Anything not clear?
Oh, so you divided it with E lah, teacher.
Not,
So,
we are plotting a different graph. So you must use your knowledge. Right? We are plotting VS. We are not plotting kinetic energy. So now we have to rewrite the equation. That's what you have to do.
Okay. Okay, teacher.
That's why the different. Yep, many things is not clear.
Not clear, teacher. Now I understood
So you have
better because
you have to do your for
homework.
next week. You have to do your 24.1 and 24.2. You should be able to do that already. Since I've gone over with you already.
Okay.
You're completed already. After that, it's just extra knowledge only.
Sure, teacher.
Right? This is your photo multiplier cell. Right? You can see very blur, one photon coming in, but right? There's a photocathode, emits electron. The electron is accelerated and then increase the number of electron. So a very dim light. At the end, you can right? Yes, you can receive a lot of current. That means you can amplify the picture. That's where it's used. In photo multiplier tube, this is for your knowledge. You don't need to know. Right? A single incident photon produces a pulse of current through an external circuit. This tube can be used to obtain picture in extremely low light level. Okay, so that's the uses. The other uses is you will see in sorry.
So I think class finished already, lah, teacher.
Yeah, I'm just finishing. Right? The other one is you see in this one is used in garage door. Open the garage door automatically for you, but you can see it being used in shopping complex, right? Where you enter a shop, then there's a sound there. Same idea, right? There's the receiving unit. There's the infrared. So as soon as you enter the room, you cut off the infrared, no current flow, so it will sound an alarm for you. Right? Or some people's house, they have above the wall this kind of gadget, so that when intruder try to climb over the wall, the CCTV in the house will notify the host that there's an intruder. Okay, so that's our uses there. So these are things that you need to know. What is photoelectric emission? Right, and then why is evidence for particular nature of electromagnetic radiation. And then all the parameters. So all these was the laws you need to remember. The graph you need to remember. Right, all the parameters. Okay, or well, draw your own. This is my own mind map. You can draw your own mind map to help you remember. Right, draw on a piece of paper, foolscap paper. Right, so we have completed all this part. Anything else you want to ask? If not, we will call it a day.
Yeah, call it a day, teacher.
Okay, if you don't have any question, we call it a day then. Okay, have a good weekend. Make sure you do your homework. If not, you will.
Cheer.
Yeah.
I've been watching your videos. It's quite good, but I think I'm going to like I can't sleep for the next few days because I have to finish so many. There's so much of videos there.
Do one by one, no? Section by section.
Yeah, I'm doing section by section, but I want to finish it fast because then
But
the
you have to
moment
do
I go
your
school, I won't have
photoelectricity
time. Yeah.
first. You have to do your photoelectricity first. The others you can leave out. This is the main important one because you lose it, it's very less efficient to go and listen and learn again. Now it's still fresh in your mind. Do your homework. You spend
Yeah,
less
sure,
time.
teacher.
That's how you should study. Okay.
Okay, sure, teacher.
Okay. Have a good weekend. See you next. You tell me when you want it. Wednesday and Thursday or Friday and Saturday. Okay.
Sure, teacher. Okay, thank you so
Bye
much.
bye.